Many of our viewers had asked us to explain the solution of a gyro numerical based on the free gyroscope. So let's talk about the free gyro question and see how these type of questions are solved. Now, solving these questions requires a basic understanding of the rational horizon diagram, which is very frequently, very commonly used to solve celestial navigation-based problems. We also need to be familiar with Napier's rules, which is used to solve a spherical triangle in spherical trigonometry. So it's a good idea to refresh these topics before we go into the free gyro topic. A free gyro is an unrestricted gyro which is placed inside an arrangement of gimbal rings, and this free gyro, the spin axis of this free gyro points towards a fixed direction in space. We can assume an imaginary star in this fixed direction, and this particular star, which is in the direction of the spin axis, is known as a gyro star. The spin axis of a free gyro follows the motion of this gyro star. So if we need to find out what is the direction in which our spin axis is pointing, we need to find out what is the direction in which the gyro star is. So with this understanding clear in our mind, let's try to understand the concept of free gyro numerical using an actual question. The question says, at 00 hours 00 minute and 00 second GMT in latitude 45 degrees south and longitude 000 degrees, spin axis of a free gyro is horizontal and pointing in a direction of 120 degrees true. At what time will it point 270 degrees true on the same day? Now these kind of questions are known as free gyro questions. You see, they are mentioning about the motion of a free gyro. Now these numericals are solved using the rational horizon diagram. We are familiar with the rational horizon diagram which we use in celestial navigation. The same rational horizon diagram will be used for solving these free gyro type questions. So let us now mark or plot the rational horizon for this particular observer. We are aware that the rational horizon diagram looks like this. You have the 4 reference points. On top we have the north, right side we have the east, at the bottom we have the south, and on the left side we have the west point. And at the center of this rational horizon diagram, we have the zenith represented by Z Zulu. Now the latitude of the observer is given to be 45 degrees south. That means the observer is south of the equator. So zenith will be south of the equinoctial, or in other words, equinoctial will be north of the zenith. Also, since our observer is in the southern hemisphere, he will be able to see the south pole. The elevated pole will be the south pole. So let's mark the pole here. You can see the pole coming up in the diagram represented by P, Papa. We can also mark the equinoctial. Equinoctial will be passing north of the zenith. Equinoctial always passes from W and E, west and east points on the rational horizon. So you see this WQE marking the equinoctial for this particular observer. Observer's position is south of the equator. So similarly, the zenith is south of the equinoctial. Now the question says that the spin axis of a free gyro is at one point of time horizontal and pointing in 120 direction. So let's identify 120 direction first. The end point represents the north direction and as you go clockwise, the direction changes to 10, 20, 30, 40. Then at point E, the direction is 0, 90. Going further, we have to go up to 120. So 120 is going to be at this particular point. So let us show our star at a bearing of 120 degrees true. Since our spin axis is horizontal, our gyro star's altitude will be 0. So that means the gyro star is going to be at the rational horizon. So let's mark our gyro star. You can see our gyro star here, the red color star represented by X-ray. So spin axis is pointing 120. The azimuth of the gyro star is 120. Spin axis is horizontal. That is why the altitude of the gyro star is 0. It is on the horizon. Also, we know ZQ represents the latitude of the observer. Latitude is given to be 45 degrees. So we have marked that as 45. And we are aware that P2Z is the colat of the observer. And in case of 45 degree latitude, the colat will also be 45 degrees. 90 minus latitude, 90 minus 45 gives us the colat PZ as 45 degrees. Now we have the pole, we have the gyro star here. Let's mark the celestial meridian of the gyro star. So you can see this is the celestial meridian of the gyro star, P2X Papa 2 X-ray. Also, since the bearing of the gyro star is 120 degrees, this particular angle, the angle Z of the PZX triangle, is going to be 60 degrees. ZS represents the south direction, 180. Bearing of the star is 120. Difference between them is 60 degrees. That is the angle Z of our PZX triangle. Now in this triangle, if you look carefully, the side Z to X is 90 degrees. Zenith is represented by Z. The star is on the horizon at point X. Zenith to horizon is always 90 degrees. So Z to X is 90 degrees. And we can now see that triangle PZX is a special spherical triangle in which we have the side ZX as a 90 degree side. So we can apply the Napier's rule. Napier rule says that if we know any two things in this triangle other than the 90 degree part, we can find out anything else. The two things which are known to us is one, angle Z of the triangle. Angle Z is 60 degrees. And we also know side PZ, Papa Zulu, which is the colat, equal to 45 degrees. So using these two values, side PZ and angle Z, we apply the Napier's rule and we first of all find out side Papa X-ray of this triangle. Papa X-ray basically represents the polar distance of this particular star. And if we do the calculation, you can see the steps coming up here. If we do the calculation, the side Papa X-ray is obtained as 69 degrees 17.7 minutes. This is a simple application of the Napier's rule. Now the question then says that we need to find out when the star is going to point 270 degrees or the spin axis is going to point 270 degrees. So let us first of all try to see the declination circle of this particular star. The star has risen at point X and the declination circle of all celestial bodies are centered at the pole and they are parallel to the equinoctial. So let's mark the declination circle of this particular gyro star, centered at the pole, parallel to the equinoctial. Let's have the declination circle. We have the declination circle of the star coming up in the diagram. So this is how the star is going to move. From point X, it is going to move in the direction shown by the green color arrow. At this particular point, it will be on 090 bearing. E point represents 090 bearing. Then it will move further At this particular point, it will have Marpas and it will be pointing north and represents the 0, 0, 0 north direction. Going further, when the star reaches here at this particular point, you can follow the laser pointer. This is where the star is going to be on 270 bearing. The W point represents the 270 bearing. So let's mark our star here and identify the star as Y. So we have the star at 270 bearing at point Y. Also, before going further, in this same PZX triangle, we can apply the Napier's rule again, and using the Napier's rule, using these two items, PZ as 45, angle Z as 60, we also calculate angle P of the triangle, the yellow color angle which you see, and this comes out to be 112 degrees 12.5 minutes. This is also a simple application of the Napier's rule. Now we have identified the star at 270 bearing at point Y. Let us now try to draw the celestial meridian of the star at point Y. You can see Papa to Yankee, P to Y shows us the celestial meridian of the star. Now if you pay your attention to triangle PZY, in this particular triangle, angle Z is going to be 90 degrees. Angle Z is 90 degrees. Pole is in the southerly direction. The star is in the westerly direction. Angle between them is 90 degrees. So PZY is also a special spherical triangle, a right-angled spherical triangle. Also in this triangle, side Papa Yankee PY is again the polar distance of the star. The polar distance of the star, which is 90 minus declination, does not change over a day. So it is practically the same. We had calculated Papa X-ray as 6917.7. So Papa Yankee PY is also going to be the same, 69 degrees 17.7 minutes. Now in this triangle also, PZY, we have two items known to us. One is PY, 6917.7. The second part which is known to us is PZ, which is 45 degrees. This is our colat. Using these two, we again apply the Napier's rule, this time to triangle PZY, and we find out angle P of the triangle. The green color angle which you see, this angle comes out to be 67 degrees 47.5 minutes. Again a simple application of the Napier's rule. Now we add these two angles, the yellow and the green angle, 112 12.5, 67 47.5. When we add these two angles, we get a total angle of 180 degrees. Now this 180 degrees is the R angle covered by the star when it is moving from point X to point Y. The star has covered an R angle of 180 degrees. Now we know that all the stars cover their R angle at a fixed rate, and that rate is 15 degrees 2.5 minutes per hour. So to cover this R angle of 180 degrees at a rate of 15 degrees 2.5 minutes, we can easily find out the time taken by the star. We divide this 180, that is angle XPY, which is the total R angle covered by the star. We divide this by 15 degrees 2.5 and we get an answer of 11 hours and 58 minutes. This is the amount of time which the star is going to take to come up to point Y when it will be on 270 bearing. When the star is on 270 bearing, the spin axis will also be pointing 270. So the time at which the spin axis will point 270 is 11 hours 58 minutes on the same day. This brings us to the end of this video. I hope you find this video useful.